Alternating current circuit summary. We're going to start with the definition of magnetic flux. Flux is BA cosine theta. That's where B is the magnetic field, A is the cross-sectional area of our loop of wire, and theta is the angle that the magnetic field makes with the normal to the area. Now we want to find out why is our voltage or EMF changing. Well, if the flux changes through the loop, then an EMF is generated according to Faraday's law, where EMF is minus N, change in flux over time. We're also going to show the calculus version of this. You don't need to know calculus, but if you do, this will show you what we're up to. But what we're really trying to get to is the result that we'll be using. So instead of delta phi over delta t, we have a derivative here, d phi b over dt. Just means you're taking a very, very, very tiny interval of time to find how the flux changes in that little bit of time. We will now rotate this loop with an angular velocity, and another term for that can be frequency, of omega is d theta dt, or, as you see it in the algebraic courses, just delta theta over delta t. Now our magnetic flux is going to continually change. Why? Because the angle that this rotating loop makes with the magnetic field continually changes. So let's just keep going with a little more calculus and then we'll be done with it at the end of the slide. So the voltage generated, or EMF, is minus d phi dt. Here's our expression for flux, nothing surprising there. And then B and A in constants, so we take them out. We have a constant loop area and we have a constant magnetic field. The only thing that's changing is the angle. And when you take the derivative of the angle, you're going to get the derivative of cosine theta gives you sine theta. Again, don't worry about that. You'll see that when you take a calculus course. And then we wind up with d theta dt, which of course is just omega. So we have this expression for the voltage generated by a loop that is rotating with an angular velocity of omega. Is it constant? No. Theta keeps changing. So the voltage will keep changing as sine theta. So the voltage will do something like this. It's a sine curve. Okay, and that's our alternating current. The induced EMF, which was shown on the last slide, varies sinusoidally with time. It's a function of sine theta, so we say sinusoidal. Got a little bit ahead of ourselves on the last one because I talked about the current, so I'll show where that really comes in now. If I connect an external circuit to this loop, and let's say I put a resistor there, I put a light bulb, what's going to happen is I'll have an EMF, I'll have a resistance, I will now have a current that's equal to the EMF over R. The current will also vary sinusoidally. So the current will do this too, and that's called alternating current. As opposed to direct current, which I had function time here and then current, direct current would just be constant the whole time. AC current varies as a sinusoid. Now I can get a greater voltage and hence a greater current by doing what? I can have multiple loops. So I can multiply the EMF by the number of loops. One of the key advantages of AC current is you can change the voltage fairly simply, and that's done in a transformer. You may have seen these on telephone poles in your neighborhood. Those are transformers. They take the very high voltage supplied by the electric company and step it down to a voltage you can use in your house, typically 110 volts. You can also find them in television sets, utility poles, which is this one here, converters, chargers for your phone. And basically what that does, metal core here, you have a primary current coming here with a certain amount of windings. Then you have a different amount of windings on the other side, which will change the voltage. So this side will be a high voltage. The lesser number of wires, you will have a smaller voltage coming out. As shown on the previous slide, a simple transformer consists of two coils of wire. One is your primary, one is your secondary coil. The coils are linked by a soft iron core, which enables a changing magnetic flux, because you have a changing current going through it, produced in the primary coil to pass through the secondary coil all at the same time. And alternating current changes rapidly. The magnetic flux in the primary coil changes, very rapidly also, which will result in eddy currents in the core as explained by Faraday's law. These currents cause power losses due to heating. That's not good. So they're engineered away by constructing the core of thin steel laminations, just thin pieces of steel with a very high resistance. Other improvements make our practical transformers, the ones you might see on the telephone pole, 99% efficient. So 99% of the energy provided by the power company, after it goes through the transformer to your home, 99% of the power gets through. That's pretty good. The different number of windings between primary and secondary allows the voltage to change. However, it keeps the frequency of the voltage a constant. So if the supply is 60 Hertz, on the secondary side, that's also 60 Hertz. The ratio between the voltages between secondary and primary is called the transformer equation. So the voltage on the secondary side over the voltage on the primary is the number of windings or coils on the secondary divided by the number of primary. If the number of secondary windings is greater than the primary, we have a step-up transformer. The secondary voltage will be greater. So whoever has more windings has a greater voltage. And if it's in the opposite, we have a step-down transformer. So you would see that again on that power line pole going to your home. The voltage current in an AC circuit continually changes as it is sinusoidal. The peak value of the wave is not a good representation of its effect on a circuit. And why is that? Well, let's say power is equal to IV. Well, we'll deal with I squared R. So we want to find the power delivered by a circuit. If you have a DC current, there's your current. You just multiply I, square it, and multiply it by R. But if you have an alternating current, what number do you use? You can't use the peak because you don't always have that current. You can't use an average because that will be 0, and you know you're delivering power. So what do? Root mean squared values, and that's what's used by voltmeters and ammeters. It's the square root of the mean value of the squares of the values of a function over a certain time. By squaring the values, we ensure that the negative voltage currents are treated the same as the positive values. So we'll be squaring all these voltages, squaring all these, okay, add everybody together, and then take the square root of it. This value, the root mean squared value of an AC voltage or current, has the same impact for power reasons as a DC voltage current of the same value. We'll just present what the root mean squared values are without going through the calculation. If we have a voltage, a sinusoidal voltage, it has a maximum value of V0, and then here's the angle, here's the frequency. The root mean squared voltage will be the maximum voltage divided by the square root of 2, or 0.707 times the maximum value. Same thing for current down here. So what would that look like? So if I have an oscillating circuit like this, and this is V0, the root mean squared value will be somewhere down here. That's going to be VRMS. And what that means physically, that will develop a certain power in your circuit. It will be the exact same power as a direct current that has a voltage of 0.707 times V0. And going forward, we will be using the root mean squared values when we do AC circuits. The voltage drop across a resistor, capacitor, and inductor were defined as follows, and this is for DC circuits. These two were covered in algebra-based physics and AP2 physics. This one for the inductor was covered in APC physics. So we have V equals IR, Ohm's law. The voltage drop across a capacitor is the charge on a capacitor divided by its capacitance. Then the voltage drop across an inductor is negative the value of inductance, that's what L is, times the change in current over change in time. Now, capacitors and inductors don't have a resistance, but they have something called a reactance, which is the analog of the resistance for a resistor. We'll start with the resistor. Let's say we have a current and voltage oscillating like this. AC voltage, AC current. The current is in phase with the voltage at all times. They reach the maximum and minimum values at the same time. And what that is saying, if I plot the current on a scale, and I plot the voltage on the same scale just with different values, the voltage will look just the same except with a bigger amplitude. This should have been over here. Where the voltage has a peak, the current has a peak. Where the voltage has a minimum, the current has a minimum. We then get the resistance is V over I, that's Ohm's law, and then the average power for the resistor, and that's what the bar is above the P and the IV, will be I squared R, where I is the RMS value, and V squared over R, where V, of course, is the RMS value. The inductor relationship is not so simple. We're going to start with the current like this, and then finding the voltage by using the minus L di dt, and then rearranging it a little bit so we change the sign to cosine. Don't worry again so much how we're doing it, but the key part is if we look at the voltage curve, and let's look at a point right over here. It's at a peak and starts to come down. The current, a little bit later, is at a peak. The current is the dashed line and starts to come down. At every point, the current is going to be shifted to the right, and we say that the current is behind the voltage by a quarter cycle. It's being shifted by a quarter cycle or 90 degrees. The maximum voltage is related to the maximum current by this equation here. V0 is equal to I0 omega L. That is the same formula as Ohm's law, where the inductive reactance, okay, this is going to be our analog for the resistance for a resistor, will be defined as omega L. Certainly left out a lot of steps here, and you could refer to another text, or Wikipedia is good for this also. We're just interested in the answers for this summary. So inductive reactance, that's the key thing. That's analogous to R for a resistor. And the other thing that's important is right here. The current lags behind the voltage. We'll now look at what happens to the capacitor's voltage-current relationship and define capacitive reactance. Here's our current, and then we find the voltage here through taking advantage of the relationship of the voltage to the charge and the capacitance. We're not showing the derivation, but this is the answer. And we have a capacitor in AC circuit. This time, the current leads the voltage. So let's take the current. Where do I want to take the current? Right here. Current's at a peak and coming down. A little bit later, and again, it's going to be that quarter cycle, the voltage is at a peak and starts coming down. So at every point, the current is leading the voltage by 90 degrees. The maximum voltage is related to the maximum current by V0 equals I0 over omega C. Again, same as Ohm's law, right? V is equal to IR, but this time the R analog will be 1 over omega C. This will be the capacitive reactance of the circuit. Let's put it all together now. We're in the same circuit. We have a resistor, an inductor, and a capacitor. We call that an RLC series circuit because they're in series and you have a resistor, inductor, and capacitor. The current through each circuit element will be in phase. This is the key part right here. Current is in phase through each of the elements. However, the voltages will be different. The voltage across the resistor is absolutely in phase with the current. For the inductor, the voltage across the inductor will lead the current by 90 degrees, and for the capacitor, it will follow or lag the current by 90. A very old way to remember this, an old mnemonic, Eli the Iceman, where E is voltage, and I is current, L is inductor, C is capacitor. So Eli says the voltage leads the current in an inductor, and for a capacitor, the current leads the voltage. Because of the different phases of the voltage drops across the resistor, inductor, and capacitor, they can't simply be added to find the total voltage. Why is that? Well, at one point, first of all, the resistance, the voltage across the resistance will always be the same. Across the capacitor, though, it will oscillate out of phase with the inductor. So the capacitor will be reaching a maximum and the inductor won't quite be at a maximum. So you just can't add the numbers, nor can you just add their RMS values because they are out of phase. And just sketch that, see if this makes a little more sense. If I have two waves, here's one wave, and then let's color the other one a little different. And the other wave is exactly in phase. If I want to add the values of them together, they're all in phase, so I can go ahead and do that. That's not a problem. But if I have something like this, that's one, and now let's do the other one, and it's slightly out of phase, it's behaving different. I just can't add them because if I add at this point, I leave one of them out because the value is 0. If I add at this point, they're both pretty high, so you're not going to be consistent there. So what we need, we have to add them as what? As vectors. And they call that a phasor diagram, like Star Trek. The length of each vector in an XY coordinate system will represent the maximum peak voltage across each element. So the maximum voltage across the resistor will be I0R. Maximum across the inductor will be I0X sub L. Right? This is the reactance, inductive reactance. And the capacitor will be I0XC, where XC is the capacitive reactance. The phasor diagram, which we have to the left, and don't worry, I'm going to explain it, represents the voltage vectors across each element, the resistor, the inductor, and the capacitor, including the phase shift. The voltage across the inductor is ahead of the voltage across the resistor by 90 degrees. So let's start at the voltage across the resistor. That's over here at a certain point in the rotation of our loops that are generating this voltage. That's the omega t. Okay, so we're just going to start the voltage across the resistor here. Okay, I'll erase that because we're going to have a lot of lines if I don't. The voltage across the inductor is 90 degrees ahead of that. That is this voltage right here, this entire line. Let me just make sure I draw that in red. And here's the 90 degrees that it makes with the voltage across the resistor. So now I'll erase that. There we go. Now let's look at the capacitor. The capacitor's voltage is 90 degrees after the resistor voltage. So that's down here. Here's 90 degrees, and it's behind the resistor. We're rotating this way, so the resistor is 90 degrees ahead of the voltage across the capacitor. We'll erase that now. We now need to take a vector sum of these quantities. So right here is the voltage across the inductor minus the voltage across the capacitor. They're in the same line, which is good, so we just have to subtract them. We then get this vector. Here's our resistor vector, the voltage across the resistor. Now we do tip to tail, and you get the final voltage right up here, V0. And again, let me erase stuff that I don't need. So we have V0, which is the resultant voltage, and it makes an angle phi that is ahead, in this case, of the voltage across the resistance. And we use Pythagoras to find the value of that. It's going to be the square of the voltage across the resistor plus the square of the difference of these two voltages, right? See, because they're in a line. One's going up, one's going down, so it's subtracted. And then we take the square root of both and we find V0, the resultant vector. We now take that voltage equation to derive the impedance. This is like a total resistance of the circuit. I replaced, each one of these had a voltage. This was VR, this was VL, and this was VC. Replaced each one with its sort of Ohm's law-like equivalent, right? Here's I0R for Ohm's law, I0 reactance, the inductive reactance, minus I0 of the capacitive reactance. And you square both of them here together. You subtract it, then square it. Factor out the I0, and I have this term here, where I have V0 equals I0 times something. Well, that something is going to be impedance. We will call that impedance. That is the vector combination of resistance, which is the opposite opposition to DC flow, and the reactance, which is the opposition to AC flow due to the inductance and capacitance. Perhaps you were questioning if this diagram just didn't blow you away a couple slides ago. What is this phi? Right? That's the angle that this voltage, which is adding up all the voltages due to the inductor, capacitor, and resistor in a vector fashion, gives you a magnitude, but it also gives you an angle. What do we call that angle? That's the phase angle phi. That's the angle by which the total voltage of the circuit leads the current. From the diagram, and we just use the definition of tangent, it's opposite over adjacent. So this opposite piece here is VL, the inductive voltage, minus the capacitive voltage. And the adjacent will just be the voltage across the resistor. Replace them with their Ohm's law equivalents. The i's cancel out, and we get tan phi, which is the phase angle, is the inductive reactance minus the inductive capacitance divided by the resistor, the resistance. The relationship between the impedance Z, R, and XL minus XC is that of a right triangle. Okay, because here was our resistance, the voltage across the resistance. Here's the total voltage, and here's the voltage, which is the difference between VL and VC. That's a right triangle. Z will be the hypotenuse, and because we're looking at this equation here that we derived on the previous slide, Z is the hypotenuse, R is the X, and XL minus XC is the Y term, and here's our phi. Matches up just with this triangle here, except just rotated a bit. From this diagram, we can see that R is equal to Z times cosine phi. We'll need that on the next slide. The average power in the RLC circuit will be I squared RMS times R. But what is our resistance here? It's not just due to the resistor, it's due to the impedance. So we replace R with Z cosine phi from the previous slide, and we now have power is equal to I RMS V RMS times cosine phi. Cosine phi is the power factor. For a purely resistive circuit, the power factor is 1, and power equals I RMS V RMS, and maximum power will be delivered to your circuit. For a pure capacitive or inductive circuit, the power factor is 0, because phi will either be 90 degrees or minus 90 degrees, and no power is delivered to the circuit. The RMS current in an RLC circuit is now VRMS over Z, the impedance. We substitute in for the impedance. We now want to find the maximum RMS current for a given voltage. That will be reached at a certain frequency of our AC current called omega 0, which is the resonant frequency. That's where you'll get the max current for an applied voltage. How do I find that? Well, V is a constant, R is constant. Omega, we want to find for what value of omega this IRMS will be maximum. Well, we can get a maximum if we just set this thing equal to 0. So we set it equal to 0, because then what are we doing? We're decreasing the denominator as much as we can, which will increase the entire value of IRMS, of the fraction. Do a very little bit of math, and you find the resonant frequency will be the square root of 1 over L times C.